Welcome back. Jumping right back into it for 1.3 multiplication. All right, so same deal as before. I'm going to go through these problems. I will pause for a moment so you can pause the video and come up with an answer on your own, and then we'll go over the answer together. Just to recap a little bit, we're going through arithmetic, even though you would be expected to know arithmetic coming into pre-algebra already, but a few things we're going to sort of rephrase and think about in a different way going into algebra. So that's the reason why we're readdressing some of this arithmetic work. So 1.7 is using the two pictures below, explain why 2 times 3 is equal to 3 times 2. Is similar to the very first question in addition. So bring on here, once again, similar to the one in addition, we just kind of flip the image. So you can see that there's 6 blocks here, 6 blocks here. These two are equivalent. They're the same size. They're just oriented differently. The picture on the left is just a rotation of the picture on the right. The size doesn't change. The first one is 2 rows of 3, and this one here is 3 rows of 2. But overall, it's still going to be 6, as you can see. So like addition, multiplication is also commutative, which means you can multiply in either order. So 2 times 3 is equal to 3 times 2. And also A times B is equal to B times A, similar to addition, where A plus B is equal to B plus A. This is called the commutative property. Once again, and again, that means that you can change the order of where you multiply. So we've been using, up to this point, we've been using this X to denote multiplication. AX B means X times B. Going into algebra, you might start seeing this dot notations, A dot B, which means the same thing. It's multiplication, just a different way of writing it. The reason for that is because we're going to be using X as a variable letter going forward in algebra, and it might be confusing to say like X times A, for example. That looks like XXA. So we don't use the X anymore going into algebra. So we'll start seeing this dot notation here. A dot B is equal to B dot A. Same thing. A times B is equal to B times A. Or even shorter here, you might see them just connected, which still means A times B is equal to B times A. When you have a variable connected to something, that means it's multiplied. One thing to note is when we were doing fractions previously to this course, you might have saw like a mixed number that is like 3 1/2, for example. Now this could become confusing as we go into algebra, because going into algebra we'll see that if you were to see something like A 1/2, this would be A times 1/2, but this is not 3 times 1/2, because 3 times 1/2, 3 times 1/2 would be 3 halves. But that is not what 3 1/2 is. The mixed number 3 1/2 is different, which is actually 3 plus 1/2. So the mixed number is actually 3 plus 1/2, which as a fraction would be 7 halves. Then that would convert to 3 1/2. So we'll go over that more when we get to fractions and things like that, but be careful with that, because I know you're used to seeing mixed numbers like this that is just written in a way it's like 3 1/2. And it's not that that's not valid, that's fine, but you just need to remember the context of what we're talking about. If we're talking about this in the form of a mixed number, then this is equivalent to 7 halves. If we're talking about this being equivalent to 3 times 1/2, which if it's written more like this, if you have a variable connected to a fraction, then that would be multiplication. So I know that could get a little bit tricky and confusing, but we won't really be dealing with a lot of mixed numbers. A lot of these here, we won't be seeing that a lot in algebra because of the confusion. So we try to avoid using mixed numbers. So if you didn't like mixed numbers, then you're in luck. Going into algebra, you won't see a whole lot of them, because it's a little bit ambiguous with what we're actually trying to do when we show a mixed number when we start to get into algebra. Anyways, that was a side rant. So we know that multiplication is commutative, meaning we can change the order just like addition. But addition is also associative, which means you can change how you group them together. Is multiplication associative? That's what we'll explore in the next question here. So counting the dots in the picture, explain why 2 times 3 grouped together times 4 is equivalent to 2 times the grouping of 3 times 4. Okay, and if you had a chance to think about that, multiplication is associative. So these would be the same value. And if you multiply that out, you would get 6 times 4, which is 24. And this here would be 12 times 2, which is also 24. So they come to be the same value. And once again, it's not a definitive proof. That doesn't mean because it worked once, then it will always work. But I can tell you it'll always work. And later on in your math career, maybe you'll go through the rigorous proof of that to show that every single combination will always be associative. We're not going to do that in this course, but I could tell you with certainty that multiplication is associative. And there are proofs out there if that's something that you are interested in. And if you were to look at these groupings, so we have 2 rows of 3 with 4 dots in each, which means that would be a total of 24, 4, 8, 12, 16, yeah, that'd be 24 dots total, no matter how you count them up. So AB grouped together times C is the same thing as A times the grouping of B times C. One thing to be careful of, though, I don't think the book talks about this very much, so I will go ahead and point it out here, is that while addition is both commutative, like this, and associative, which means A plus B plus C is equal to A plus B plus C, right? This is commutative property. This is associative property. And multiplication also is. So A times B is equal to B times A. That's the commutative property. And also A times B times C is equal to A times B times C. And that is the associative property. Okay, because we know that all of these are true, that does not mean that they're commutative with each other or associative with each other. So if we have something like A times B plus C, and let's say it's grouped together like this, okay? Because multiplication is associative and addition is associative, that does not mean that they're associative with each other. So we cannot do A times B plus C. We cannot do this. That would be wrong, and you would not get the same answer for that. So just wanted to note that out because I think the book doesn't explicitly say that they are not associative or commutative with each other, only within themselves. All right, so knowing those properties, let's go ahead and compute this problem here. And try to make things easy for yourself, knowing that we can multiply these in any order that we want. Okay, so the order that makes this easiest for me anyways is I see a 25 and a 4. So 25 times 4 is 100. 125 times 8, well, let's see. If we have 2 125s, that's 250, which means if we have 4, then we have 500, which means if we have 8, we have 1,000. So we've got 100 here, we've got 1,000 there, and then we're left with 4 times 6, which is 24. Wait, did I do it? No, we already used the 4. We used that, so we're just left with the 6. So we have a 100, we have a 1,000, and we have a 6. And that gives us 600,000. Okay, so in the picture below, explain why 2 times 1 is equal to 2. Okay, so this one is pretty simple. You multiply anything times 1, you're going to get the same number. So if you remember back in the last section, we said that anything plus 0 gives us back the same number. In this case, 1 is that value for multiplication that if you multiply anything times 1, you get the same number. Not 0 in this case, but if you use 1 and multiply anything times 1, you get the same number back. So the reason for this is, what multiplication is it's repeated addition, right? So 2 times 3 is adding 2 3 times. So it'd be 2 plus 2 plus 2, right? You have 2 3 times. In this case, if you have 2 times 1, you're adding 2 1 time. So 2, and then that's it. You're just done. It's just 2. All right, let's go ahead and compute these two. Once again, remember, you cannot use the associative property across addition and multiplication. All right, so actually, that's what this problem is showing, that you cannot do that. 5 plus 6 would be 11, times 7 would be 77. If you do this one first, that would be 42, plus 5 would be 47. So they are not the same. Again, I mentioned this before, and multiplication is associative. Addition is associative, but multiplication and addition are not associative with each other. I said a couple slides ago that the book did not really address this very much, and never mind that, they do. My memory was bad. But this is a side note. This is something that the book, this is not in the book, but something that I thought might be a good reminder. If you remember your order of operations coming into this course, you should know which operation to do first, and that would be multiplication would go first. So then you would get 5 plus 42 would be equal to 47, which would be the same as this one here. So this grouping right here is sort of unnecessary because these parentheses, like, that's what we would have done first, even without the parentheses. So I just wanted to note that. Okay, using the picture below, explain why the left side is equivalent to the right side. All right, so this one's a little bit trickier to explain using the picture, but if you could see on the left side, there are 2 sets of 3 plus 4. All right, so that's what this side of the equation is saying that there's 2 sets of 3 plus 4. And you can see here's a 3 plus a 4. There's a 3 plus a 4 here, and there's a 3 plus a 4 here. Right, and that's going to be 24. Did I do that right? I'm sorry, 14 total. And the right side of the equation, there are 2 3s and 2 4s. So there's a 3 here, a 3 here, and a 4 here, and a 4 here. But again, we can see that overall they make the same shape. They get the same answer. So those two are equivalent. This is what's known as the distributive property. I don't know if you noticed here, but the left side of the equation is 2 times 3 plus 4. And then, so we get an extra 2 here. So there's 2 2's here on the right side, and there's only 1 on the left side. But what we did was we distributed this 2 across this grouping right here. So we did 2 times 3, and then we did 2 times 4. So 2 times 3 plus 2 times 4, that's called the distributive property. And we can see that written out right here. So if we have A times grouping of B plus C, that would be the same thing as saying A times B plus A times C. Or, again, because multiplication is commutative, we can put this part here on either side of the parentheses. So we can do A times B plus C, or we can do B plus C times A. So it doesn't matter if it's in the front or if it's in the back. It would come out to the same thing. We see B times A, but we also know that that's the same thing as A times B. In algebra, we might see it written like this without the x's, as I mentioned before. Just kind of this A smushed against this parentheses means multiplication. Whenever you see a variable pressed against something, that means we're using multiplication. So A times B plus A times C, or AB plus AC. Again, there's a video here. And all the videos will be in links in the description below. If you want to go check those out, I recommend that you do. All right, so another one right here. So this one, knowing what you know about the distributive property, see if you can come up with a with a cool solution to this one. If you notice, there's not anything to distribute, right? It's not like you have something to multiply across a grouping, but you can still use the distributive property just in reverse. So give that a shot. And the way you do that is instead of just multiplying this out, you can do 51 times 9. I know you know how to do that. You can do 51 times 31. I know you know how to do that. And you can add them together. But there's a much easier way to do that. You can just reverse the distributive property, because look at this. It looks like 51 has already been distributed. You have a 51 here and a 51 here. You can just reverse that out. And what would that look like if you undid that distributive property? You would get something that looks like this. You pull that 51 out of both terms, and then you're left with 9 plus 31. So 51 times 9 plus 31, and now you can just add together the 9 plus 31, and that's easy to do. And now you're left with 51 times 40. Now 51 times 40, now how do we do that in our head? Probably do that if we think hard enough, but I think it's easier just to do 50 times 40, because 5 times 4 is 20, then 50 times 40 would just be 2,000, right? But you know that this is 51 40s, and 2,000 would be 50 40s. That'd be 50 40s right there, right? And we want 51 40s, so we need another 40. So we know that that's going to be 20 40. All right, what is the value of 17 times 13 plus 51 times 13 plus 32 times 13? All right, same deal as before. They're just an extra term, but we do see that we have a 13 here, a 13 here, and a 13 here. So go ahead and try to use the reversing of the distributive property once again here. All right, and as you notice, it doesn't matter how many terms you have. You can still do that. And to prove that we can do that, if you're not totally sure if you can do that with 3 terms at once, just do it with 2 terms at once. So just look at this part of it, because we already know, we've already done it with 2 terms before, and go ahead and pull the 13 out of that. So then if we pull the 13 out of that, we're left with 17 plus 51. We got a 17 here and 51 here, times 13. So then we're left with this. We can't forget about our last term here. That we haven't done anything with that yet. So that's still there. But we have our 17 plus 51 times 13, and then we still have that other one. But now you see that, and if we put a dot right here, just to remember that that's multiplication, we know we have a times 13 here and a times 13 here, so we can do it again. We can just add that 32 into that one right there. Or we want to add that first, just to make it really look like it's 2 terms. 17 plus 51 would be 68. And now we're left with 68 times 13 and 32 times 13. And that's very obvious that we can do that again. So we didn't need to do that extra step. We could have just pulled 13 out from the very start to be 13 times 17 plus 51 plus 32. But I just wanted to show you that if you weren't too sure if you could do that, just do it one at a time, and it becomes clear that this becomes 68 times 13 plus 32 times 13, and then you can just do it again. So in that case, if you did it that first way, then you'd be left with a 68 plus 32 times 13. 68 plus 32 would be 100, times 13 would be 1300. Once again, we have this video here down at the bottom, and link is in the description to get an extra explanation on that. Okay, consider the multiplication facts below. Find a pattern, and assuming that the pattern continues, predict the answer to the last multiplication. All right, so we probably already know what 0 times 7 is. If you're coming into this course, you probably already know what that is, but let's just recognize the pattern first. First, you see this counting down. First, they're all times 7. And it's counting down by 1, 5, 4, 3, 2, 1. Once again, as we said in the last couple slides ago, that multiplication, we know, is just repeated addition. So this is 5 sevens, this is 4 sevens, this is 3 sevens, this is 2 sevens, this is 1 7. So you know that each one we go down, we're doing 1 less 7. All right, if this is 5 sevens and this is 4 sevens, we know that we're just adding 1 less 7 here, which means we're going down by 7. We're going down by 7 each time. 35 to 28, 28 to 21, 21 to 14, 14 to 7. And if we continue that pattern, we know that we're going down by 7 again, which would make this 0. We also know that if you multiply anything times 0, then you get 0. Because just like I said for multiplying by 1, if you did repeated addition for, let's do 2 times 7, that would be the same thing as, not that. That would be 7 plus 7, right? That'd be adding 7 2 times. If we do 1 times 7, that would be adding 7 1 time, which would just be 7, right? If we added 0 7 times, that would, well, we can't even write 7 because we're not even doing it 1 time. So what's here? Nothing. So it doesn't make sense for 0 times anything to ever be anything. So once again, we're not going to be doing a rigorous proof for this, but know that if you multiply any number times 0, you're going to get 0 because it wouldn't make sense for it to be anything else. All right, and that's it for 1.3. So once again, at the end of the chapter, or at the end of the section, there are more practice problems. I recommend you go through and do those for extra practice. And that's it for this one. We'll see you next time for 1.4.